Brilliant sponsored this video. More brilliant later. Yes, you heard me right. A graph does have eigenvalues. The study of a graph's property using linear algebra is called spectral graph theory. This field of study is huge and fascinating, but the most fundamental idea of spectral graph theory is simple and beautiful, easy to understand. Let's take a look, shall we? Here is the outline of this video. We will talk about some basic graph theory. Then we will do a review of linear algebra. Next, we talk about the graph Laplacian and some of its basic properties. Then we move on to the Fiedler value and the Fiedler vector. At the end, we talk about probably the most famous application of spectral graph theory in machine learning, spectral clustering. Now, let's get started. A graph G is made of vertices and edges. The collection of vertices is denoted as V, and the collection of edges is denoted as E. For example, this graph has 5 vertices denoted as V1 up to V5, and it has 6 edges denoted as tuple or tuples of Vi, Vj. For example, V1, V2 means there is an edge between vertex 1 and vertex 2. Generally speaking, the edges can have directions. It's just like on social network. I follow you on Instagram, but you may not follow me back. In this video, we make the assumption that the edges are unidirectional. It's like a genuine friendship. I'm your friend, then you are my friend. The graph is also called undirected graph. The degree of a vertex is the number of neighbors or connections of the vertex. The vertex with the highest degree is like the most popular guy in your social bubble. Suppose I remove 2 edges from this graph. I'm intuitively decreasing the level of connectivity of this graph. But if you look at this graph and the original graph, they have something in common. They're both connected. A graph is connected means that I can start from any vertex of the graph and reach any other vertex, following a sequence of edges. Intuitively, the more connected the graph is, the shorter the path may be. Removing one more edge, there is no way to start from vertex 5 to reach vertex 2. We say this new graph is disconnected, but it has 2 connected components. Alright, let's quickly examine some typical graphs' degrees. The isolated vertices form a valid graph, but the degrees are all 0. Vertices of a line graph has degrees of 2, except those 2 vertices at the end. The cycle graph is highly symmetric. It has equal degrees for everyone. An opposite extreme example is a star graph. It has a high level of imbalance of degrees. A complete graph, or fully connected graph, is like a utopia of degrees. If there are n vertices, then each vertex has the highest possible degree, n-1. For a general disconnected graph, usually there is no pattern to follow. This graph is also a good example that we cannot reconstruct the graph using the degree information only. For some special cases we can, like this one and this one, but not generally. Can you find another graph that has exactly the same degree information? To capture all the connectivity information of a graph, we need the adjacency matrix A. Aij is defined as 1 if there is an edge between vertex Vi and vertex Vj. Take the first row as an example. It means that vertex 1 is connected to vertex 2, vertex 4, and vertex 5. Because connection is mutual, therefore the first column is exactly the transpose of the first row. If we sum each row of the adjacency matrix and align them along the diagonal line, we get the so-called degree matrix. A lot of information is lost during the summation process. This agrees with our observations that you cannot use the degrees to construct the graph. Let's look at the adjacency matrices and the degree matrices of the graphs we mentioned earlier. Although those matrices look very different, but they do share 2 characteristics in common. First, both matrices are symmetric, which means they equal their transpose. Second, all the entries are real numbers. We call such matrices real symmetric matrices, and they have some very nice properties. For the disconnected graph with proper labeling, we see a block structure in the adjacency matrix. This block structure has a big impact over the matrix's eigenvalue and eigenvectors, which we will discuss deeply in a moment. Alright, that's everything we need to know for the graph side of the spectral graph theory. Now let's look at the spectral side. Spectral theory, in general, is a huge topic that spans across several fields of mathematics. However, if we focus on finite dimension linear space, square matrices, spectral theory becomes a theory of eigenvalue and eigenvectors. So what is spectral graph theory? It is a study of eigenvalues and eigenvectors of graphs matrices. As we assume the graphs are all undirected, so all the matrices associated with the graphs are real and symmetric. Real symmetric matrices are so good. Why? First, the real symmetric matrices are guaranteed to be diagonalizable. A matrix is diagonalizable means that we can find two matrices P and lambda such that the matrix can be written as P times lambda times P inverse. Lambda is a diagonal matrix here, and for real symmetric matrix, the eigenvalues are all real. Another great property of a real symmetric matrix is that the symmetry is preserved under addition or subtraction. For example, D minus A gives us a new matrix, L. It is called the Laplacian matrix. We will talk about the Laplacian matrix very shortly, but now let's review three important properties of the eigenvalues and eigenvectors. First, 0 is actually a valid eigenvalue, but 0 vector is not a valid eigenvector. The highlighted eigenvector is the corresponding eigenvector for eigenvalue 0. It is essentially the solution to the homogeneous linear equations, because the right-hand side of the equation is essentially 0. But an all-zero eigenvector doesn't make any sense, as the eigenvalue can be any number. The second important property is about orthogonality. Eigenvectors of different eigenvalues are orthogonal to each other. Here, I'm using different colors to represent different pairs of eigenvalue and eigenvectors. Two vectors being orthogonal means that their dot product is 0. If you take any two eigenvectors and find their dot product, it is indeed 0. The last important point to review is multiplicities. The same eigenvalues may have different multiplicities. For example, in order to find the eigenvalues of these three matrices, we solve the characteristic polynomials. We find out that the first matrix has two different eigenvalues, but the second and the third matrices have 2 as the only eigenvalue. The times that the eigenvalue appear as roots in the characteristic polynomials is called the algebraic multiplicity. Algebraic multiplicity is not the only multiplicity. Taking a closer look at the second matrix, we see that the eigenvalue 2 has 2 corresponding and orthogonal eigenvectors. It means the eigenspace spanned by the eigenvectors has a dimension of 2. The dimension of the eigenspace of the eigenvalue is called the geometric multiplicity of the eigenvalue. But when we try to find the two eigenvectors for the third matrix, we have trouble. 1, 0 is a valid eigenvector, but we cannot find the second eigenvector that is orthogonal to 1, 0, which means the eigenspace only has a dimension of 1. Putting these examples together, we see that the algebraic multiplicity is always greater than or equal to the geometric multiplicity. Can you spot the difference between the first two matrices and the last one? The first two matrices are both diagonalizable. This is great news for our degree matrix and adjacency matrix, because they are symmetric, therefore they are always diagonalizable. For the rest of the video, I will just use the word multiplicity, as we will limit our discussion to real symmetric matrices. Still remember the Laplacian matrix? L equals D minus A, the degree matrix minus the adjacency matrix. The Laplacian matrix is the difference between two real symmetric matrices, so it is also real and symmetric. Therefore, all the nice properties we discussed earlier will also apply. First, let's see what will happen if we multiply a vector f. We use f instead of v for two reasons. The first reason is that I don't want to confuse you with v for vertex or v for vector. Second is that we will see the f vector does have a meaning of a function that is defined on the graph. Let's check the ith component of the new vector lf. We will see that it's actually the summation of the difference between fi and its neighbors. Again, please bear with me with the notation. I'm writing fi and fj as if f is a function instead of using the subscript. I promise you that the reason will become clear later when I explain why the L matrix is called the Laplacian matrix. Okay, suppose f is eigenvector, then we have Lf equals lambda f. Therefore, lambda equals f transpose Lf. Substitute the expression of Lf, we see a very interesting expression. Simplification by staring at it is not for normal people like you and me, so let's expand it. For this particular graph, using the adjacency information, the summation can be grouped into 4 components. Simplifying one more step, we see that the eigenvalue lambda can be written as a summation of squares. Just by observing this result, we can have a few important conclusions. First, L is positive semi-definite. It means all the eigenvalues of L are non-negative. Second, 0 is always an eigenvalue of L. We can simply citing f as a constant. The last observation is more hand-waving. For a given graph, the smaller the eigenvalue is, the smoother the eigenvector is. It is true because the smaller the difference between entries of the eigenvectors, then the smaller the summation is. On the other hand, if a vector happens to be the eigenvectors for 2 graphs, then the one with a smaller eigenvalue is less connected because you have fewer terms to sum over. Now let's turn those intuitive observations into concrete examples. For the isolated vertices, because there's no connection at all, therefore lambda equals the summation of nothing, therefore the only eigenvalue is 0. And we can find 4 eigenvectors that span the eigenspace of dimension of 4. Our first non-trivial example is a line graph, and we have 4 different eigenvalues. For a better visual understanding, let's plot those 4 eigenvectors and see how smooth they are. As we mentioned earlier, we can always pick a constant vector as the eigenvector of eigenvalue 0. And the first non-constant eigenvector has a smooth decreasing trend. You can verify it yourself if you consider the connectivity information in the graph. The third and the fourth eigenvectors do have bigger and bigger variances. Now let's move on to the cycle graph. The cycle graph clearly has a stronger symmetry, and this symmetry is revealed in its eigenvalues and eigenvectors. The eigenvalue 2 has a multiplicity of 2, and its 2 eigenvectors do look symmetric. Also, look at the fourth eigenvector. It is a vector that tries to maximize the eigenvalue, isn't it? Next, let's move on to the star graph. The star graph is the perfect example that when we interpret the eigenvectors, we have to take the connectivity information into consideration. For example, why the eigenvector corresponding to the largest eigenvalue 4 is smoother, or at least looks smoother, than eigenvector 2 and eigenvector 3? The reason is that vertex 1 is at the center of the graph. All we care about when we talk about the difference is the difference between vertex 1 and other vertices. And from this perspective, eigenvector 4 is the most rough one. Another good example that symmetry impacts the multiplicity of eigenvalues is a complete graph. The complete graph only has 2 eigenvalues, 0 and n, where n is the number of vertices, and the multiplicity of n is n-1. My intuitive way to make sense of this multiplicity is to think about the permutation. We can verify that 3, -1, -1, -1 is actually an eigenvector for the eigenvalue 4. And because of the symmetry, I can redshift the entries to get 2 more eigenvectors. Therefore, the dimension of the eigenspace is at least 3, but it's not 4, because the 4th eigenvector will be linearly dependent on the first 3. Therefore, the multiplicity is 3. All good? Now let's move on to our last example, the graph with 3 connected components. This one is particularly interesting because the eigenvalue 0 has a multiplicity of 3, which is exactly the number of connected components. Look at the first eigenvector. It seems that it's only non-zero on the first connected component. The same idea applies to the second and the third eigenvector corresponding to the eigenvalue 0. This is truly interesting, and a more interesting question to ask is what information is hiding in the eigenvectors corresponding to other non-zero eigenvectors. To answer these questions, it is beneficial to understand first why the L matrix is called the Laplacian matrix and what it does when we apply the L matrix over a vector. Most likely, you and me know this man Laplace for two reasons. First, the Laplace transform. Second, the Laplacian operator. As we are not doing any integral, so likely we need to focus on the Laplace operator. The Laplace operator calculates the divergence of the gradient of a function. In Cartesian coordinate, it is the summation of the second partial derivatives. For one-dimensional case, it is just the second derivative. Therefore, for a linear function, the Laplace of this function is 0 everywhere. Imagine you are standing on this function at 0.5, 0.5. You look at your neighbors in a small interval. Because the second derivative is 0, the amount your right neighbor is higher than you is exactly the same amount that your left neighbor is lower than you. But imagine a non-zero Laplace. A negative second derivative means that you are higher than the average of your neighborhood. You have much lower left neighbors than higher right neighbors. And it becomes the opposite when the second derivative is positive. The same idea applies to higher dimensions. We can construct a function whose Laplace is positive almost everywhere. From this angle, it's very clear that the average function values in a small neighborhood is always larger than the value at the center. The most naive understanding of the Laplace operator is that it measures the discrepancy between a function's value and the average of its neighborhood. Now you can understand why I use f instead of v to denote the eigenvector. Imagine f is a function defined on the vertices. Its neighborhood is restricted by the edges. Take vertex 2 as an example. When we apply the Laplacian matrix on f, the second entry of LF is essentially the sum of the differences between vertex 2 and its neighbors. This is almost the Laplace operator if we find the average of it. And of course, there is the so-called normalized Laplacian matrix, which essentially divides each entry by the degrees. We are not going to use the normalized Laplacian in this video, but you can convince yourself that it does exactly the same thing to a function defined on the graph as the Laplace operator does to a normal function. Now let's look at our first eigenvalue 0. It turns out that the Laplacian matrix L has eigenvalue 0 with multiplicity k if and only if the graph has k connected components. To gain some intuitions, let me bring back those examples again. For the isolated vertices, it's easier to think about the multiplicity from the algebraic perspective. Therefore, 0's multiplicity is 4. For the cycle graph, it's easier to think about it from the geometric perspective. Treat the eigenvector as a solution to the linear equations. The 4 independent restrictions limit the dimension of the eigenspace to be 1. Let's prove it more rigorously. First, let's prove that the multiplicity of eigenvalue 0 is no less than the number of connected components. We already see that with proper indexing, we can find a block structure in the Laplacian matrix. Indexing is just assigning an order to the vertices. We are free to index however we want, so the block structure will always exist. Now, we can construct eigenvectors whose corresponding entries of the block are non-zeros. This shows that if there are k connected components, we can have at least k eigenvectors of eigenvalue 0. Next, let's prove the opposite using contradiction. If there are k connected components, because the eigenvalue can be written as the sum of squares, therefore it can be written as the sum of 3 sum of squares. Each of them has to be 0, so we can construct k independent eigenvectors just as before. Suppose there is one more eigenvector. Because eigenvector cannot be 0, therefore it must be non-zero somewhere. If one entry is non-zero, it is impossible to keep your neighbors 0. Therefore, our extra eigenvector cannot be linearly independent of our existing eigenvectors, which creates a contradiction. Sounds good? Let's move on to the second smallest eigenvalue. To make life easier, let's focus on the connected graphs. Recall that if the eigenvalues are different, the corresponding eigenvectors are orthogonal. Here, I'm using subscript to indicate that f1 is the eigenvector corresponding to the first eigenvalue 0, and f2 corresponds to the second eigenvalue. A zero dot product suggests that the summation of entries of f2 is 0, but different from f1, there will be up and downs in f2. Lambda 2 and f2 are called the Fiedler eigenvalue and the Fiedler eigenvector. They are named after mathematician Miroslav Fiedler. So why are lambda 2 and f2 so important that they have their own names? Take a look at this graph. Let's calculate its Fiedler eigenvalue and Fiedler eigenvector. Lambda 2 is 0.36 and f2 is on the screen. Notice that the indexing is completely random, therefore our L doesn't have a block structure, but we will see that it doesn't change the nature of the graph. It seems that the Fiedler vector finds a very nice partition of our original graph. If we reconstruct the block structure, the partitioning is more clear. The Fiedler vector finds a choke point, the edge between vertex 3 and vertex 4. Intuitively, vertices 1, 2, 3 form a community, and vertices 4, 5, 6, 7 form another, and the edge 3, 4 is the only connection between these two communities. Because lambda 2 is non-zero, but it's also the smallest eigenvalue. Therefore, f2 will behave like a pair of scissors. It's going to find the weakest connection in the graph and flip the signs of the entries of f2 there. But this mechanism can easily break down. For example, why should I cut on this graph? The Fiedler vector is not a solution to an artificial optimization problem. Just by the nature of a linear system, the Fiedler vector happens to do a reasonably good job when the graph is well behaved. Not this one. We can fix it by dropping the weightless edge assumption. We can assign weights to different pairs of vertices to measure how close they are. In real life, this often breaks the symmetry. For example, you must have 1 or 2 closest friends. The new Laplacian matrix has a new definition, but the core idea remains the same. Because vertex 1 is closer to vertices 2 and 3, so this time these 3 will form a new community. And the Laplacian matrix also reveals a stronger affinity between vertices 1, 2, and 3. As we mentioned earlier, the Fiedler vector is not artificial, but we can frame it as an optimization problem. This direction naturally leads to the following question. How about other eigenvectors? They are all orthogonal to the previous ones. What information do they carry? Does this idea look familiar? It sounds like principal component analysis. If you forget, perhaps you can check the sponsor of this video, Brilliant. This is my dashboard. By the time I make this video, I have been using Brilliant for several weeks, and you can see I'm learning computational biology. Brilliant is great for 2 reasons. First, it's designed for visual learners and players. Take PCA as example. To know which direction has the largest variance, it's much easier to slide the slider rather than conceptualize it in your brain. This is me learning computational biology. The second advantage of Brilliant is that it provides a to-the-point direct introduction to the STEM fields that you are interested in. For example, I don't need to install Python, I don't need textbook, I just open the browser and I'm learning computational biology. If this sounds good to you, use my link to register for a 30-day free trial and get 20% off on the annual premium plan. You have nothing to lose and a lot to explore. Back to the searching of eigenvectors. The process does look like principal component analysis, but in the context of spectral graph theory, this process has a new name, spectral embedding. The motivation of PCA and spectral embeddings are different. PCA is designed to perform dimension reduction, and as we saw earlier, spectral embedding can perform graph partitioning. And in principle, PCA can only work on covariance matrix, while spectral embedding can work on any similarity matrix, including the adjacency matrix and the Laplacian matrix. Let's look at one application of spectral embedding, spectral clustering. We will follow Andrew Ng's third highest cited paper published almost 23 years ago. The dataset we are going to use is two-dimensional. PCA doesn't work because we have rotational symmetry. Also, any further dimension reduction will lose too much information. Running k-means directly will lead to a result that doesn't agree with our intuition. To quantify how close the data points are, we can define the affinity matrix. The affinity between 2 points P1 and P2 takes an exponential form controlled by the hyperparameter sigma. From here, the L matrix defined in the original paper is actually not the Laplacian matrix, it is the identity matrix minus the Laplacian matrix. To avoid symbol confusion, I'm going to call this matrix K, and let's see how K depends on sigma. A larger sigma will increase the global level of connectivity, while a smaller sigma will punish the longer distance heavily. In real life, we don't see this block structure, otherwise the problem is already solved. Choosing the right hyperparameter in machine learning requires a lot of experience and sometimes a little bit of magic. Let's check the eigenvalue and eigenvectors. The first three eigenvectors already correctly identify different components in the original graph. We can see that the eigenvectors try to behave like a constant in different components. The next step is to put these three eigenvectors together and use the corresponding entries to build a new vector p tilde to represent the original data point. As we anticipate, k-means algorithm on p tilde returns perfect result. And the last step is to use the label we just obtained to label the original data point. This is dream level perfect result. Now is a good time to stop this video. If you want to know more about spectral graph theory, you can find the references in the description. Thank you so much for watching. Please consider building a directional edge.